Yeah, and thank you so much for having me today to talk with you guys about um, electrification in the grid. Um, the policy direction in California and really, um, much more broadly nationwide in many other countries as well is that electrification of buildings and transportation is going to be one of the most cost-effective and expedient ways for us to achieve our decarbonization goals. So, given that most buildings connect to the grid to get their power, it's important that there's a close working relationship between the power supply and um, the buildings that draw from them. So at SCE, we're very active in working with the building community to kind of understand, where the building sector is headed and how we can support that transition. So we're going to talk today, somewhat general terms in a large way about kind of the general trend toward electrification, how grids everywhere are starting to decarbonize at different rates, and of course it's different from state to state what the mix is, but there's a general trend. A lot of information we'll talk about today that's California specific. And then as we really get into some of the details about strategy and planning, we'll be talking a bit about more about what SCE's efforts are and not necessarily representative of all utilities. However, there's a lot that's happening industry-wide to move in this direction. So, and feel free to put questions in the chat as I go, and as I have moments to pause, I'll try to address those as we go. But again, thanks for having me, and we'll go ahead and jump into the presentation formally. So, and I'll kind of pepper these. The intent of this presentation is to provide you with background that helps both you as practitioners to kind of better understand the broader context that the projects you're working on will kind of interact with, but then also questions that your clients and your other stakeholders will have as you're working on these projects that you may or may not feel comfortable addressing. So hopefully there's some additional sources of information and references that will be useful to you as you have those conversations on your projects with your clients and customers. So, kind of high level, I think this audience is pretty well versed in what the features of an all electric home are, but it's always good to have a quick little reference for context. Primarily when we're talking about getting fossil fuels out of the home, we're talking about space and water heating, and then some of the other appliance type uses like cooking, clothes dryings, and then electric vehicles are critical, and then solar and battery storage systems, particularly where the home's orientation and layout lends itself well to those systems. Um, so that's the key features in terms of offsetting what in California at least is traditionally um, fossil fuel driven appliances. Elsewhere in the country, the penetration of electric is different depending on the type, supply, and cost of electricity. But we won't really get into that today. And I know that a lot of the practitioners here work all over the country, different parts of the state. So there may be questions or kind of nuances about kind of the different power mixes in different areas and different rates of decarbonization. But again, we're looking primarily at California here. So one of the questions that comes up frequently is the conventional wisdom for a very long time was, you would rather burn gas on site than burn gas or another fuel at a power plant, and then have those generation losses, transmission losses, and then run a like an electric resistance type of heating appliance, whether it was cooking, space heating, water heating, etc. That was maybe true, 15, 20 years ago and before, but there's been a number of changes in terms of the power supply and a major shift in terms of renewables and storage and the deployment of wind, solar, and batteries that's really changed that picture in terms of what the overall um, carbon makeup of the grid is, as well as the efficient technologies we mentioned for the all-electric home that we'll look at a little bit more closely here in a second. But you can see roughly around 2012, 2013, the cost metrics of solar really took off, and there was a real tipping point where the deployment of solar really started to explode onto the grid. And today, in terms of total supply, we're nearly 60% carbon neutral on the grid in terms of our supply, and getting cleaner every year by a couple of percent on average. So that includes all sources that don't provide or don't give off carbon. So whether that's solar and wind and other qualifying renewables, or large hydro and nuclear, those count towards kind of the carbon reduction targets that we have. And these trends are continually accelerating over time in terms of the deployments. Year over year, we're seeing significant penetration of additional solar and wind. So we continue to move on this target. And the goal is statewide that we want to be 100% clean electricity by 2045. And that's through the legislature, that's by statute. And so the utilities are following what the state has directed as their goal. And so as part of that, SCE undertook a white paper looking at a data-driven analysis of what it will take us to meet the state's targets and get to that 2045 carbon neutrality goal. And then to understand that in order to, once we have that grid as clean as possible, we want to power as much as possible on that grid and transition away from fossil fuel end uses and power them with that clean electricity. We've recently updated that analysis. This was done probably about, I think, 4 or 5 years ago. We released that pathway. And based on recent or policy implementation that's happened over time, the electrification provisions in Title 24, the Air Resources Board's scoping plan that sets specific targets for phase out of the sale of things like fossil-driven space and water heating appliances, as well as targets for the phase out of the sale of new internal combustion vehicles. We've actually increased the penetration projections for 2045 based on that, and that's affected kind of what the overall analysis is, as well as the feasibility of certain generation technologies that'll get us to that 100% carbon neutral power by retail sales. We predict that there will be a doubling of rooftop solar over that time in the next 20 years, a tenfold increase in customer-owned storage. There will be a significant increase in electricity consumption, but as we'll look at in the coming slides, that doesn't necessarily mean an 80% increase in infrastructure. There will definitely be significant infrastructure needs to support this, but they're not necessarily proportional with usage because of the diversity of the types of end uses, and seeing more usage spread out outside of the peak periods, which allows our infrastructure to be used more efficiently. So we'll talk about that as we move forward too. And we'll also see reduced cost pressure as that efficiency of the overall system allows us to deliver electricity even more efficiently at all hours of the day, so that we're not just, we're spreading out more usage over the same infrastructure, provides, lower cost pressure overall. And then the efficiency of these end use technologies compared to other fuel types also drives some of that potential cost reduction over the course of the transition. And then if we, let's see here, sorry. There we go. So just an overall look from and this is from the Air Resources Board GHG inventory, you can see where some of the targeted sectors in terms of the overall carbon emissions currently for the state. Electricity, a little over 16%, buildings 10%. Overall, because buildings use about 75% of the electricity in the state, most of that red and yellow sector you see there is attributable to buildings. And then transportation is a huge piece, and we'll touch on that today, not in extreme depth because we're focusing on passive houses, buildings, but there's an interaction in that most residences are going to afford some form of vehicle charging more and more as we move into this transition as well. So that's, you can see a pretty big lift, and there's a lot of places that where we deliver power is going to impact that overall GHG emissions across the economy. And I like to show this graph. I know it's a bit of an eye chart, but just to break it down, this is basically the entire U.S. economy's energy flows in one diagram. The LBNL, the Lawrence Livermore National Laboratory, they provide these energy flow diagrams, and it is quite instructive to show kind of where the different sources of energy nationwide are, where they go in terms of their end uses. But what I really want to highlight, and what's really important to kind of take away, is just how inefficient our current, didn't, sorry. There we go. How inefficient our current energy system really is. Because really what we primarily care about is this energy services, this useful work, this dark gray box. In order to get there, we waste a lot of energy. If you look at the flows from all of the different combustion sources we have, which still nationwide are, 2/3 or more of the total energy supply, those fossil fuel energy sources, they reject, anywhere from 2/3 to 3/4 of the energy that they, their energy potential in terms of waste heat. Um, so what we are trying to do when we're moving to the clean energy economy is both shrink this light gray box by using energy sources like renewables, which have much fewer losses in generation and well, about the same in transmission, but a lot less in um, generation. And of course, there's less transmission loss if you're distributed generation. So rooftop solar, of course, if it's used close to the source, there's less transmission loss there, of course. But also potentially shrinking some of the useful work box by using efficient end use appliances. So that is things like heat pumps, which, as probably most of you are aware, are extremely efficient because they're not converting chemical energy. They're just using that refrigeration cycle to move heat from one place to another, whether it's in heating or cooling mode, because the systems, at least in space conditioning, are reversible. They're 300% or more efficient depending on ambient conditions. Gas furnaces in electric resistance typically top out around that 95% efficiency. So heat pumps are a major silver bullet in this transition for the clean energy economy, and figures into that overall energy picture significantly. Same thing with cooking technologies. Gas cooktops, you only get 40% of the useful energy out of those. The rest is heat that goes into your kitchen or out the vent hood. Um, Electric resistance countertops are about 0.75%, right, or 75% efficient, and then induction cooktops are up to 90% efficient. Really directly directing that energy where it needs to be in an efficient way with instant on and off. And then finally, electric vehicles, significant efficiency compared to their internal combustion counterparts, just highlighting that, typically with all the different engine losses and other losses in an internal combustion vehicle, you're only getting about 16 to 25% of the input energy out as useful work, whereas with electric vehicles, because of their efficient transfer of electricity and the regenerative braking, you're up to 90% efficient with those technologies. So overall, it's important to understand that we don't have to displace all of the primary energy from fossil fuels, because we can use the energy so much more efficiently with these end uses and deliver it very efficiently with clean energy, whether it's distributed energy or at the grid scale. So we can shrink both boxes in that Sankey diagram. Okay, so the question also comes up though, like, what about resiliency? Don't we want to have multiple fuels in case there's an outage? So that comes up a lot. It's important to note that outages, they are are inconvenient, they are impactful. I know that right now with some of the wildfires we're having and the wildfire conditions, even today, we have potential for outages and people that are impacted um, as we enter that season. But nonetheless, significant progress has been made over the past 5 years to reduce the frequency and duration of outages. SCE and other utilities have made significant efforts and investments in grid hardening to strengthen the grid against extreme weather events and the impacts there. Measures like covered conductor, which we've installed tens of thousands of um, uh, miles of conductor across the uh, uh, the whole grid to protect it against those types of vulnerabilities, as well as things like fast acting fuses, high definition cameras, weather stations that provide real time on the ground data. So we have a much more resilient grid than we did just 5 years ago. It's important to note too that with any utility system, over time repairs and upgrades are going to be needed to maintain. Outages can't ever fully be avoided, but when we have planned outages, efforts are always made to isolate the outage areas as closely as possible to where the work's being done and to reduce impacts to those that are affected. Um, the metrics on average, and of course this is average, so some customers will see more and some less, but on average, typical SCE customer experiences an average of one outage per year for approximately 2 hours. Um, and where customers are impacted in high fire areas or are relying on medical equipment, they have access to programs which provide discounted backup systems or no cost depending on their qualification in terms of income and the risk area. But it's very important to keep in mind that modern gas appliances require things like electronic ignition or electronic controls, which don't function if the power goes out. Um, it's also important to note that you may be able to technically light a gas stove with a match if it's a newer model or an older model, I mean, that maybe doesn't have the electronic ignition and controls. But it's not a great idea any more than it would be to roll your propane grill into your kitchen and start cooking with that. It's important to maintain proper ventilation when you are doing combustion cooking inside. And that's recommendation from the American Medical Association, Lung Association, and others. And then keep in mind also that if you're fueling a vehicle, if there's an outage in your area, gasoline pumps, if they don't have power, they won't be able to supply gasoline similar to chargers. So you would need to drive to a functioning pump the same way you would need to drive to a functioning electric vehicle charger. So just some considerations there. One of the great things that code is mandating for new construction is solar and battery for homes, or I should say solar for homes plus future battery, so battery readiness. Multifamily, there is a prescriptive requirement for battery, but that can be traded off through the performance method. So, but the opportunity there is that you can potentially size that system to provide your basic needs using that critical loads panel, using that solar and battery system. So that's an opportunity to be able to build resiliency into your buildings as you construct them. Yeah, and then folks often say, well, are EVs going to be a liability for the grid? Well, there's a number of ways that EVs actually function potentially as a resiliency asset when they are capable of providing um, you know, they have plugs or can do vehicle to load. So there are a few manufacturers that have that capability. This is an example of one where there was an outage in this contractor's neighborhood, and he ran some extension cords from, he had a Ford F-150 pickup, did his house and his neighbor's, a couple of refrigerators and deep freezers. His neighbor had exotic fish in a giant aquarium that he, needed to keep running so that they wouldn't potentially perish, and then kept the internet and the Sega Genesis and screens and PCs going for all the kids so that they wouldn't think the world was ending. But after 6 hours of all of that load connected to his Ford F-150 Lightning, his battery was down only 5% from where it started. Um, and that's a vehicle load example. We're going to be likely seeing the capability for the vehicle to have bidirectional charging that can power directly to the building, similar to the way that a stationary battery would function, and potentially even vehicle to grid, where that power is sent out to the grid as well. So there's different levels, and the technology is coming along, but that's something that we'll see in the coming years as a bigger and bigger value proposition with electric vehicles that will not necessarily add to the problems for the grid, but help actually solve them. So the questions come up, about some of these periods. Late summer usually is when we see them, when we get alerted through the Flex Alert program that the grid is a bit constrained. We're seeing heat waves. We're seeing other conditions that can challenge what the current capacity of the grid is. And as demand approaches what that capacity is, we work with customers with programs like demand response and others to try to manage to that peak so that we don't have issues with having to do the last resort of things like proactive shutoffs in certain areas, just because of capacity concerns. So that question comes up. Are these added loads going to be a problem and expand the periods where we have to be cognizant of coming up against demand? So one of the really beautiful things about electric homes is that while they do tend to have some impact in terms of the overall peak usage, it's fairly modest in terms of, the usage increases more significantly than the peak usage does. And this is a study from the Sacramento Municipal Utility District and that territory where they looked at a fairly significant number of gas hybrid homes and compared those to all electric homes. They had more gas homes, so that there's a higher number. But they looked at where the peak amperage fell for those homes, and it was probably about somewhere between 15 and 20% higher peak load on a home by home basis for the all electric home, which is somewhat to be expected that you have more end uses, so you have more things drawing electricity. But it wasn't a doubling or a tripling, and even in those cases, they didn't see any homes that peaked at higher than 80 amps, which was a very interesting finding. So yeah, the takeaway is that yes, there is increased usage at the home level, but because of the intermittency of those end uses, it increases the diversity factor in the load calculations, which allows you to have more connected load, but not necessarily all used at the same time. And then having the capability to flex some of those loads, like water heating, like electric vehicles, allows you to shift those in response to price signals or other considerations, to move those outside of those peak hours and reduce that impact. Here is another graph showing the annual neighborhood impact at the transformer level of an all-electric neighborhood compared with a similar mixed fuel neighborhood. These were SCE studies. The grid graph shown here is in Fontana, but there was a similar development in the Irvine area that demonstrated again that even though you definitely see more usage and more kind of like off season peaks with the all electric neighborhood, but those winter, spring, and fall peaks don't really exceed what the traditional peak would be for a mixed fuel neighborhood. That they're very comparable during the summer season, which is cooling dominated. Now, I know that there's people on this, or practitioners that work in other areas of the country. If you don't have a cooling dominated grid, then there may be some nuance to this, that you may see some seasons like winter with increased peaks. But at least for Southern California, where we have cooling dominated, um, uh, that cooling kind of drives um, those grid peaks. That's a consideration, that it creates a lot of capacity the rest of the year. So moving right along. Um, so the large, significant deployment of solar has over time led to this phenomenon called the duck curve, which, again, I'm sure a lot of folks here are pretty dialed in and somewhat familiar with that. But the duck curve is this trend over time where additional solar over the course of the day creates this this significant drop in kind of net demand in the middle of the day, which flip flops the traditional. It used to be when it was primarily a one-way grid interaction, and primarily driven from fossil fuel baseload. The peak used to be, like 2 in the afternoon. Now it's shifted to where it's more in the evening, and this ramp up that we have, starting about 4 p.m. and going till 9 p.m. when the sun's going down, but a lot of residential uses are ramping up, and the temperatures are still quite warm in the afternoon. That's where we have that kind of flex alert period. So it's usually a handful of days in this late summer and early fall, but uh, that period, that 4 to 6 p.m. period, is really where that peak grid infrastructure is targeted. The good news is that technologies like batteries are being deployed at a very rapid pace, almost exponential in terms of the total deployment. Nearly half of the nation's installed battery capacity is in California. So we've been a leader in grid side battery capacity deployment. And as of April of this year, we surpassed 10,000 megawatts installed grid side battery capacity, which is pretty substantial, pretty big milestone, given that just 5 years ago, we had less than a gigawatt. We had about 700 and change megawatts of installed grid capacity. So that's a huge amount of growth in a fairly short period of time. And what that has meant is that we continually have been seeing records in terms of what we're able to do to address that peak. So this is a screenshot from late April 30th, I believe. This was the California statewide grid. And we saw that the dispatch of battery in that evening set a record. This has since been broken. I think the current record is 7.5 or 7.6 gigawatts, set a couple weeks later. But that was the first time it peaked over 7 gigawatts of actual deployed power. Just 2 weeks before that, batteries had peaked over 6 gigawatts for the first time. So in 2 weeks, it went up a whole gigawatt in terms of actual deployment. So I know we have more capacity than that, but part of it is dependent on how much they can be charged over the day by the excess solar that charges those batteries above and beyond what the load that customers are calling for in real time during the day from this kind of large available solar, wind, water that we have during the peak of the day. But it's worth noting because for a 2-hour period on April 16th, batteries were the predominant source of electricity on the grid, meaning that even though the sun wasn't shining, solar power was the predominant source of electricity on the grid at that time. And that was something of a milestone because that shows kind of the progress we're making towards that vision of a clean energy future, that it's kind of unfolding before our eyes, and year over year making significant progress and passing milestones. And that's going to continue over, year over year to continue to grow and continue to address that neck of the duck and allow for that kind of overall expansion. I'm going to pause for a sec and look at the chat window. Sorry. Let me just, oops. Oh, now it's not letting me do that without going out of presentation mode. If there's any questions in the chat that I haven't addressed, please let me know. Sorry, because I can't see the chat window while I'm in presentation
Oh,
mode.
okay. Let me just share the chat for you. If you click
Yeah.
let me see how I can.
Oh, wait, I
On
think
the
I might be
bottom,
able to
yes.
do it.
On the bottom, the second icon, you have chat. So you
Okay, so there are
can.
some questions in the chat. Okay, let me just look here real quick before I get all the way to the end. um, okay, how much will building energy efficiency improvements reduce site and grid GHGs? Silver BB. So yeah, I just want to make the note that building energy efficiency improvements are still very much critical, very important, and that pairing a good, efficient HVAC system like a heat pump with really excellent envelope performance is really important, because energy efficiency is a decarbonization strategy as much as electrification is. Anything that gets us to use less energy, um, and be able to kind of coast through those temperature extremes is helpful. So I don't want to minimize the importance of energy efficiency at all. Are the slides going to be made available? I I sent a PDF to Passive House, so they're welcome to distribute it. Um, let's see here. Are most battery systems big enough to run HVAC for days? The upper percentiles of outage duration now are probably on the order of days, depending on the CA region. So yeah, we talked a little bit about the average duration, and certainly there will be portions of the our territory and others where there may be protracted outages, particularly if there's an extreme, weather event that causes a disruption. Um, a wildfire taking out poles or something that need maintenance or need to be replaced. Those sorts of things can lead to larger, longer duration outages. And that goes back to, the solar and battery where you can recharge the battery is going to be really helpful. I think there's ways to, to fully run an HVAC system to condition a whole house may take a battery that could be uneconomical, depending on the size of the house and how efficient it is. But you may be able to run, like uh, portions of the HVAC system, particularly if you have a mini split and have a area of refuge that allows that capacity to serve it. It's going to be very much case by case, but again, this goes back to that question about efficiency. If you have passive house design principles implemented, you're going to be able to coast through those types of events, and just sip energy to be able to maintain livable comfort conditions over protracted periods of time. So uh, it's going to be very situational and very specific to your particular dwelling. But you have to look at those economics and the design on a case by case basis. There's a question about how much hydro is projected to decrease. So the existing hydro resources are expected to be there year over year, depending on how wet of a rain year we get, impacts how much hydro is available. Um, so uh, there's a variability seasonally from year to year that will be impacted by if we have dry years, we have less hydro available to us. Um, hydro can be a major player in terms of energy storage because pumped hydro, where during the day when there's that abundant energy, it's able to be pumped back up to reservoirs when we have an abundance of clean energy, and then that water can then be let down through the turbines to generate electricity again, basically storing that gravitational potential energy. So hydro is a major component of energy storage in addition to kind of chemical batteries. Question about transformer level peak demand overload at the neighborhood level related to homes upgrading service from 100 to 200 amps. Essentially, the concept that if enough of your neighbors upgrade their service, then you may be locked out of that option without paying for a transformer upgrade. So typically, one house isn't going to be required to upgrade that transformer for the whole neighborhood if they're like the last one, right? Because that once you're outside of the building envelope, the responsibility goes to the utility. Um, the sizing of um, infrastructure may be impacted more typically for new construction, but in terms of local capacity, um, that's not usually going to be the trigger. Um, there could be impacts with timing where those infrastructure upgrades may need to happen if you have enough neighbors that have upgraded. But we have a tool that you can look at to look at what circuit capacity is at the neighborhood level online called Dr. PEP, DRPEP, and that's something where you can look at the circuit level of to what the capacity is and see if there is an issue. Um, and that's something we look at in our planning processes to understand where those upgrades need to happen proactively so that we can accommodate folks that want those upgrades as they happen. There's a question about span smart panels, main panel with a meter to allow load balancing, allow homeowners to keep existing service. Is there any issues with these type of meter panel boxes? So smart panels are a great strategy for being able to uh, manage those loads and make sure that you stay within kind of that peak amperage. And then, where are the plans to create? Okay, so there's a question that actually gets to some of my upcoming slides. So I'm kind of caught up with the questions, and I'm going to go ahead and go back to the presentation, which there's just a couple more slides, so I'm close to the end. Yeah, I just wanted to point out that some of the planning processes that Edison has in place to proactively plan for the coming electrification. As we noted before, our Pathway 2045 and the updated countdown to 2045 predicts that this transition is happening and the rough timeline where it's happening. And we have goals for deployment along the way to serve that and to be able to provide the power where people need it when they need it. The grid and the way we manage it is going to transform in the very near future. Our vision for how that's going to happen is laid out in this white paper called Reimagining the Grid. It's going to be a lot more reliant on interactions with customers and the way that customers use energy on site and the way they flex what we call distributed energy resources, things like solar batteries, EVs, heat pump water heaters are an example of a potential distributed energy resource that can be controlled and shifted on the customer side of things to better address how that building interacts with the grid. We estimate about $5 billion per year in grid investments to support the technologies and the upgrades that are going to enable this transition. As we become more dependent on electricity, we need to make sure that we're diversifying and maximizing the way it's supplied to customers. We talked a little bit about the potential for electric vehicles to be a grid asset. There was a study that Redwood Energy did. Some of you may be familiar with them. They're in Northern California, and they do a lot of electrification projects as well as research. They estimated, these numbers are from roughly a year ago, but the total battery capacity in all of the vehicles registered in California compared to how much fixed residential storage and even fixed utility storage at the time, and now this number is roughly doubled, but the number of vehicles has also increased significantly. But that at the time, if you considered that the average commute for somebody, daily commute is about 40 miles, and then people want a certain amount of reserve range, roughly 80 miles. That still leaves over half of their battery capacity on average, and that total available capacity that could potentially be used for vehicle to building to reduce demand or vehicle to grid potentially as that technology matures where they can interact with the grid and supply power, stored power to the grid during constrained times. It's actually more than what was at the time the total grid capacity of storage. So the potential and the promise there is very significant, and it's something that we have pilots to look at how that's going to work, what rate structures might support it, and what technologies will enable customers to take advantage. Then to that question of power lines with new higher capacity lines, here's a couple of different technologies that we've been looking at deploying that'll support that. Advanced conductors in particular, that's a picture on the lower left. These are upgraded conductors that have a stronger composite core that minimize sagging, and a trapezoidal aluminum subwire that allows more current to be transmitted. So they can operate at higher temperatures, carry more capacity, and minimize sagging. So they can as much as double the capacity in existing lines. They can be deployed through maintenance as opposed to new building permits. So they can be provide capacity where it's needed, potentially at lower total cost than new lines, and much more quickly because the permitting process is much easier. Another strategy is dynamic line rating, where instead of having a maximum load rating that is based on extreme conditions and locking that in at all times, looking at the real-time conditions along different parts of a line and being able to increase the capacity based on current weather conditions that would enable a more dynamic type of capacity rating for those lines. So these are just some of the strategies and technologies that are being deployed to kind of get us to where we need to be as cost effectively as possible. And then the final slide I wanted to point out here is just going to that concept of the advanced planning and forecasting. So we're working very closely with different industries, like one of our major sectors is going to be the transportation sectors we talked about, and the medium heavy duty kind of goods movement sector is a kind of a major area that we're working to make sure that the corridors that support those types of industries are going to be able to deploy the necessary infrastructure to support electrification in those areas. So looking at geographically where that's likely to happen, looking at where our constrained circuits are to upgrade those over time, and also looking at which circuits currently have capacity to accommodate this, so we can work with industry to push growth into those areas as much as possible, and be able to provide that in real time. So there's a lot of work being done, both in terms of the way the technologies are going to support this, as well as how we're going to change our processes to be able to have more forward thinking to accommodate the new paradigm. So that is pretty much what I had today. Hopefully it covered a lot of the questions folks have. We didn't get into a lot of the kind of building level technologies, but a lot about how buildings and the grid are going to interact, and the expectations there. I don't see any newer questions that I haven't addressed yet, but if there are any, either people could come off mute at this point and ask them, or just put them in the chat. I know we have just a couple minutes left.
The call to action that I would describe for you is we want to do things. Passive is the important things to do first, and you can do the other things later as you go on. Once you know better, then do better, as we say, that's there. And in terms of supporting Passive House California, we appreciate it. We have a newsletter at passivehousecal.org. You can sign up for the newsletter. You can take an individual professional membership, an organization company membership. You could potentially be a sponsor, donor, or volunteer. And the passivehousecal.org is how you get there. We've got thank you for your time and attention. The things you learn that you share with you is that this light is lighting all of the others around it. So thank you for the time and things that you have spent there.